Hello, in this video we will review thermochemistry, a blast from the past. I've learned that students tend to learn a little bit of thermochemistry and then forget it, and then come to second semester of Gen Chem and have no idea what's going on when we assume that you know it. So let's review. So these are things from chapter 14, particularly energy, enthalpy, and enthalpy of formation. So, gotta go big picture first. Energy is the big ticket. It's the capacity to do work. And this work could be, say, expansion or contraction of a gas, which is what we dealt with in the first semester of Gen Chem. It could be other forms as well. Electrical energy is another one that comes to mind from a chemical reaction, which we'll get to later in this course. Okay, so that's energy. The total quantity of energy in the universe is assumed to be constant, the law of conservation of energy. And what this means is if you, say, release energy from one process, it's going to be absorbed by some other process. It always goes somewhere. Now, one of the ways that energy is transferred is by heat. And so heat is the transfer of thermal energy between two bodies at different temperatures. So you have a hot thing, a cold thing, they reach some average temperature. The hot thing transferred heat to the cold thing, and that's heat. Heat is not temperature, right? Temperature is a measure of average thermal energy in a sample, and heat is how you transfer that thermal energy. And then this overall study of energy and converting between different forms is called thermodynamics. And then when you do it specifically for chemistry, we tend to call it thermochemistry. And either one of these terms is okay here. I don't really nitpick between the two. Okay, when we're doing thermochemistry, we often define system and surroundings. And this is very arbitrary. The system is whatever we care about. The surroundings is everything else. And so the system could be your entire solution, and the surroundings is the rest of the universe. Or your system could be molecules inside the solution, and then the solution itself and the rest of the universe are part of the surroundings. Well, however you want to define it for a given problem. If your process is exothermic, your system gives heat to the surroundings. Heat out is exothermic, exit out. Heat in is heat that's absorbed by the system, supplied by the surroundings, and that's endothermic, enter, N. Now there's sign conventions for this. Heat out is negative, whereas heat in is positive, right? So exothermic heat, so heat leaving the sample gives you a negative Q, heat entering the sample gives you a positive Q, and then the same is true for work, and we'll talk about work more in a minute. Work out is negative, and so this is expansion of gases. So this is work done on the surroundings by the system. That's negative. And work in is positive, and that's work done on the system by the surroundings. So, for example, compressing a gas is work in. And so these sign conventions are pretty important. Now, many of these thermodynamic functions are state functions. And so what this means is it means that your change in that function is purely determined by the final and the initial. So we can do this for a lot of different things. Total energy is equal to final minus initial, the change in total energy. The change in pressure is final minus initial, change in temperature, so on and so forth. And in chemistry, we always define this as final minus initial is the change. And so these are called state functions. And elevation is another example of that, when potential energy depends on elevation in a geographical sense. In that it doesn't matter how you walk from the bottom to the top of the mountain, your change in elevation and your change in potential energy is the same, and that's a state function. This is in contrast to an energy transfer function or a path function, which is how a system transitions from one state to the other. And so, for example, taking the long way versus the short way up the mountain give you different lengths that you walk, so your energy transfer or your path function looks different. And so heat and work are examples of this, in that how this transfer is made will give you potentially different amounts of heat and work, and so you have to keep that in mind. You cannot do final minus initial for a path function. It just doesn't work to talk about work that way. All right, so an analogy here is that, see the puddle on the street? Well, that's not rain on the street. There's water on the street. The rain is the means by which the water was transferred from the clouds to the street, so it's a transfer function. Okay, let's continue on. So we defined this before. In Gen Chem, we limit ourselves to talking about energy changes made through heat and work. And in terms of work, we talk about expansions or compressions of gases. Right? So this is change in total energy of the system. We use U for this because E is kind of it's a letter that's used a lot. And we want to make sure that we're clarifying that this is the internal energy of the system and not some other form of E. And so we use U for that. So the change in the total internal energy of the system, which is the big ticket item that we want to know usually, is equal to, equal to heat plus work. And then work is pressure times the change in volume with a negative sign to make the sign conventions work out. Okay, so that's how we define changes in energy, heat plus work. Now we have two scenarios. Say you're doing this and the volume is constant. Well, your change in energy is equal to the same equation here, but delta V is equal to 0 because your volume is not changing. 23 liters minus 23 liters gives you 0. So this whole term here goes away, and then your total energy change is just equal to your heat. And then we put the little subscript on here to denote heat at constant volume. Because heat is an energy transfer function, it might be different if you're, say, at constant pressure. So we just label it to be clear. So if you do your chemical reaction inside some giant steel container that's not going to change volume, any heat that's released is related to your total energy change of the system. Now, another scenario, say the pressure is held constant. So then we're dealing with enthalpy. So let me define this. So we have the same equation we did before, and we can't really do anything with it because sure, the pressure is constant, but it has some value. And the change in volume is not 0 necessarily. So we can't really just neglect this term anymore. We have to deal with it. And now we're kind of stuck. So what we do is we just, in effect, make up a term called enthalpy and set it equal to heat at constant pressure. So if we rearrange this equation in terms of heat, and now it's heat subscript P because it's heat at constant pressure, and then we define enthalpy to be basically just equal to this heat. Right, so here's U, here's PV. We define the function without the deltas in it, and then you can put the deltas all the way through. The definition holds either way. If you're at constant pressure, you can factor this pressure out of your final minus initial, and that looks like this. And so basically, enthalpy is just heat at constant pressure. Since typically we do chemistry at constant pressure, because our systems will be either open to the atmosphere or the same pressure as the atmosphere, we wind up dealing with enthalpy a lot. So that's why it gets the letter H. It's pretty much heat, assuming you're at constant pressure. So that's enthalpy. We use that a lot. So let's compare these a little bit. So if you have heat at constant volume, that's internal energy. If you have heat at constant pressure, that's enthalpy. And one question though, internal energy and heat are state functions. Q is not. How are they equal? And the reality here is that we defined the path for both of these. Heat at constant volume is a defined path. Heat at constant pressure is a defined path. And by doing that, we can make heat equal to different state functions depending on how we define the path. Okay, so that's enthalpy. Enthalpy is useful because to a large extent it is heat and we want to know about heat. Is this going to melt things? Is this enough heat to, heat my water heater? Whatever, right? We care about heat. And at constant pressure, that is enthalpy. So when we're dealing with the reaction, we often have, reactants to products. Here's a reaction. And then your enthalpy change, which is a state function, we can do just products minus reactants. So if you were to know the absolute enthalpy of your products and reactants, then you could just subtract them and get your change. But we don't know absolute enthalpy. How much heat does this have? That doesn't make any sense. So we have to do something with that. And that's what this enthalpy of formation thing is that we talk about next. Before I get there, I got to point out this degree symbol. It refers to a standard state, pure compounds at 1 bar of pressure. This is especially important if it's a gas, but still needs to be at 1 bar, even if it's a solid. If it's a solution, then it's 1 molar. And so this is our standard state. We got to define pressure in order to make this whole thing work. Okay, so given that standard state, we can now set a reference. We want to know the change between the enthalpy of one thing and another in our reaction. So we need to have a way to kind of define what is the enthalpy of this thing. And so what we do is we set some arbitrary reference to be the elements in its most stable form. And now we can then deal with changes from that. So this is the standard enthalpy of formation, which is defined as the enthalpy change to form 1 mole of compound from its elements. That's what the F means. It means formation. And then the degree sign is the standard state we just talked about. So we pick our reference, elements, to be 0, and then enthalpy of formation is however much heat at constant pressure it takes to make some product, some reactant, some compound from its elements. So for example, graphite, its enthalpy of formation is 0. It's the most stable form. For diamond, this form of carbon is not the most stable form of carbon thermodynamically, and so it will have some enthalpy of formation value, and a bunch of other compounds have enthalpies of formations as well. So this choice of defining enthalpy of formation equal to 0 is arbitrary but super convenient because it kind of makes sense. Elements, that'll be the base form. And now elements in their normal physical states is important too. For oxygen, you're dealing with O2 gas because that's its normal state. Now this idea is similar to defining sea level as our global 0 for elevation. So Mount Everest, its height is determined as a difference to sea level from, I'm guessing, the nearest sea. And so its height would be 8,850 meters from sea level. But say you use Dead Sea, the lowest point on Earth, relative to mean sea level. If you use that as your 0, well then Mount Everest is now taller, right? So the height of Mount Everest is the same in absolute sense. It's just how we measure it is different and depends on what we choose to be 0. Another thing we could choose to be 0 is the center of the Earth. And since our Earth is not quite spherical, if you chose distance from center of the Earth as your metric, then Mount Chimborazo in the Ecuadorian Andes is your tallest mountain. It is farthest from the center of our Earth. But we don't do that, we use sea level. Okay. Now the reason why this is important is we can use these enthalpy of formation values to determine the standard enthalpy of reaction. And that's useful. So we should note that it is the standard state, so it's 1 bar and 1 molar. And then, okay, we can take final minus initial. We can take products minus reactants. And we can take the enthalpy of formation of all the products, same for all the reactants. You add them together, and then don't forget to multiply by the stoichiometric coefficients. And so if you had, say, this made 2 CO2 gas, you need to take the enthalpy of formation of CO2, multiply it by 2. In effect, what we're doing here is we know how much it takes to make one compound, how much enthalpy it takes to make another compound, and we're just comparing the difference. Say my house is some elevation above sea level, your house is a different one. We can define our elevation change as just our difference from sea level. And so that's in effect what we're doing here. And so you can look up these enthalpy of formation values in tables, in your book, in reference manuals, things like that, and then use that to find your enthalpy change of some reaction without having to do the measurement. And that's useful. The main reason why I put this in here now is because we do this same thing with entropy and Gibbs free energy, which we talk about in this chapter. And I want you to remember how to do it for enthalpy because we're going to do the same thing and just change the letters. Okay, hopefully most of this sounded familiar, and if not, go back and read the relevant sections in your book and get ready to go to then build new content on top of this. Thanks for watching.